LearningMeasure.tv, a science and engineering podcast with emphasis on measurement, brought to you by David Archer and LearningMeasure.com. Episode 50, Ionizing Radiation.
Hello, I'm David Archer, owner of LearningMeasure.tv and LearningMeasure.com. LearningMeasure.com is an online training website with emphasis on measurement and test, as well as engineering and scientific topics. When you register as a student at LearningMeasure.com, you have immediate access to all the courses marked free in the course catalog. But if you want to take the remainder of the courses in the catalog, you have to get a subscription, which is $5 a month or $60 a year. I'd like to announce some courses that have been added to the course catalog since the last time, which are Physics 53, Angular Velocity and Angular Acceleration, Physics 54, Introduction to Torque, Angular Momentum and Rotational Energy, and Measurement 272, Introduction to Torque Measurements. These are all courses that have been asked for in the past, and we've started to build a series of courses around them. It's been a while since we've done a last podcast. We have been doing a lot of things which to the website and other things that have been taking up too much of my time. And another announcement on Learning Measure. If you've noticed, there has been a lot of changes. There is a place now where you can edit your student profile. That's where you can input your resume, designate your employers or your educators if they're using it. And that's at www.learningmeasure.com/docs.profile. You can change all your settings there. Also, there's a new My Programs page, which is similar to the My Courses page, except it shows what programs you've signed up for. Reminder, programs are collections of courses. When you go to the My Programs page now, it'll show you what programs you've signed up for and what courses you have yet to complete in order to finish that program. That's something that people have been asking for. One thing that a lot of you have asked for is ability to pay for just one course at a time. We're working on that. We're going to make it so that you can access a single course for $5 for 3 months. And so you could purchase courses one at a time. If you really wanted to do that, at $5 a month for all the courses or $5 for access for one course for 3 months will be the next option. We're going to make some changes to the interface a little bit. The course catalog is, I've got a lot of feedback that the course catalog listing all the courses on one page is too much. So we're going to break it down so that we're going to list all the categories on one page and then take a second step to go to the courses in that category. I'd like some feedback on that if that's what you want to do. We haven't done it yet, so and we've got some other things we're trying to do. With all the stuff in the news lately, I've actually had a request from one of you to do an episode on ionizing radiation and how it's measured. So that's what we're going to do. If you ask for it, we'll do something. First of all, I want to talk about what is ionizing radiation. Matter is made up of atoms, and atoms basically have in their center particles called neutrons and protons. Protons are positive charged particles. There's also things called neutrons, and around this nucleus, there's these cloud of electrons which are negatively charged. When you atoms are electrically neutral, but if you put enough energy into an atom, you can knock out an electron. And when you knock out the electron, that's called ionizing the atom. So ionizing radiation is basically any type of radiation that can knock electrons out of atoms. Now, there are 4 basic types of radiation that most people know about. One of them is called alpha radiation. What alpha radiation is basically an ionized helium nucleus. It's basically 2 protons and 2 neutrons. So that's what that is. It just shot out of the nucleus of an atom in radioactive decay. Another type of radiation is called beta radiation. And it's just an electron. An electron shot out of the nucleus and from some radioactive decay process. And then there's what's called gamma radiation and X-rays, which is just this is light. Electromagnetic radiation. And of course, another thing that can pop out of the nucleus is something called a neutron, which is something about the size of a proton that can ionize an atom. These all happen in radioactive processes in the nucleus, and they have enough energy when they shoot out to ionize an atom. So how do you measure it? Well, first thing, when there's radioactive decay, it's a exponentially decaying process. That means if at some initial time, the number of particles at some time is equal to the number of particles initially at time 0 times e to the minus t over tau, where tau is called the time constant. So when t equals tau, it's 1 over e times the initial value. So that's what the time constant is. How long it takes something to decay 1 over e times what you had originally. But most people, because it's an easier concept for some people, we often specify the decay rate, or the exponential decay, in terms of what's called the half-life. And that's the time it takes to reduce the number of atoms by half. What is the time constant in with respect to the half-life? We want n of t over n0 equal to 1/2. That means half of them are gone at that time, equals e to the minus t over tau. Well, you can solve that fairly easily. So it's basically, you take the natural log of both sides. So you end up with minus natural log of 2 equals minus t over tau. The half-life then, solving for t 1/2 equals tau ln2, natural log of 2. So now if you know the amount of material you have at some time, and you know its half-life, you can solve for the time constants, and then you have this expression to say how much you have left at any time. Now this is for just one thing, and it can get complicated because you could have stuff that decays into the stuff you're looking at, and it could decay into other stuff, and it can get more complicated, but this is the simplest case. Now that just tells you how much you have at a given time. What often you want to know is the decay rate, is what's the change per unit time. Well, change per unit time it's dn dt, the change. It's a derivative. Now, if you don't know what a derivative is, well, that's okay. The result's the important thing. So you take the derivative of this, right? It's going to be n0 minus 1 over tau e to the minus t over tau. And that gives you the number of decays per second. So if you know the number of decays at a certain time, you can get the number of decays at all other times per second. So what we're talking about now is units of decay is, oh, this is our cat. I don't know, he shouldn't have gotten in here. I don't know how he got in here. Oh well, we'll just let him, or her, actually, make a statement of some sort, I guess. Oh, she wants to be petted. I think we can keep going and let the cat lay on the table. The number of decays per second, which is that derivative you just saw, one decay per second is called a becquerel. That's the SI unit of decay rate. So a becquerel, named after, now when you write a unit that's named after somebody, you write the unit with a lowercase letter, but when you abbreviate it, it's with a capital letter. So the unit of decay rate is the becquerel, and it's 1 decay per second. Becquerel was kind of the first person to discover, one of the first persons to discover radioactivity. He was exploring fluorescence in materials. You know, if you've seen fluorescent minerals, you know that they'll glow in the dark, basically. And there were these substances that when film was exposed to them, it would create images. And he thought it was a fluorescence phenomenon until one day he put basically some rocks in a drawer with some film, and he noticed that even after way past, if they've been in the dark for a long time, they couldn't be fluorescent phenomenon. It was still producing images on film. The next one, famous person that involved in radiation is Curie. Curie also is another unit of decay rate, CI, and it's roughly equal to 3.7 times 10 to the 10th becquerel. Way bigger unit. Just historically, that unit came first. The other thing about radiation, these are rate, decay rate. How many decays per second? Well, when you measure radiation, another type of thing you might measure it with is a Geiger counter, which measures counts, particles per second, counts per second. But it's not decays per second, because not everything that decays reaches the detector, so that could be a complicated thing. But you could also measure this in counts per second from a Geiger counter or something, but there are all kinds of factors to turn that into like becquerels or curies. Well, you know, it's ionizing radiation. So there was an older the way to measure the effect of ionizing radiation is how much air does it ionize, just air at standard conditions. And the SI unit doesn't have a name. It's basically the coulomb per kilogram. Oops, sorry. That's not the coulomb. It's a coulomb. Yes, it's a coulomb per kilogram. Or charge per unit mass of air. Well, there's an older unit called the Roentgen, which is some weird number, 2.58 times 10 to the 4th coulombs per kilogram. So that's ionization. Well, the other way that really people are concerned about people's health. So it's not really the amount of ionization that matters there. What matters is how much energy is absorbed by the body. So a more relevant unit is what's called absorbed dose, which is the amount of energy absorbed per kilogram, energy per unit mass. And the SI unit is the gray. Now this is named after somebody named Gray, unit GY, which is equal to 1 joule per kilogram. That's a gray. It's SI unit of absorbed dose, the amount of energy absorbed per unit mass. An older unit called the radioactivity absorbed dose, or RAD, is a somewhat smaller unit. It's not the SI unit. It's 100 rads equals 1 gray. And this is absorbed dosed. Well, that's probably not fine enough. I mean, that you can define precisely. But one of the issues is that all types of radiation don't affect all humans the same way. For instance, 1 gray of gamma rays gives a different effect in a body than 1 gray of alpha particles. So they tried to come up with a unit that gave the same effect on tissue as X-rays or gamma rays. And that unit is called, the SI unit is called the Sievert. It's also named after a guy, Sievert. And its abbreviation is SV, capital SV. It's 1 gray, equivalent of 1 gray of gamma rays in tissue, in human tissue. There's an older unit, the REM, I think it's the radiation equivalent in man, which is another smaller unit, 100 REM equals 1 gray, or 1 Sievert, I should say. So this is under the thing of under the name equivalent dose. So you've got units of decay rate, Becquerel and Curie, decays per second, or some large number of decays per second. Ionization in air, coulombs per kilogram, or Roentgen. Absorbed dose, joules per kilogram for the gray, or 100 rads per 1 gray. And equivalent dose. Well, how do you get equivalent dose? Basically what you do is you take the absorbed dose and you multiply it by a factor depending on what type of radiation it is to give the equivalent dose, to give the same effect in humans as gamma rays. Now more than ever, we really want your feedback on what to do on the site, because we're making a lot of changes soon. And the more feedback we can get, the better. Or a suggestion for an episode, you send it to suggestions@learningmeasure.com. And we do have a Facebook page and a LinkedIn group. But there's many ways you can get information back to me. So right now I really want some feedback on what to do next for you on this site, and what courses to develop, what changes to make. I mean, we want to have you have a bigger input, so please send us an email or contact us any way you can. All right, that's it for now. Bye.